Hello everyone, hope you guys are doing good. Today we are going to complete the discussion on path planning of robotic manipulators. So let's quickly do that. In our previous lecture, we have pretty much completed the potential field method. And in that we realized that there are going to be two types of potentials. One, what we call attractive potential, which is going to allow the robot to start from a starting location and eventually reach to the final position. Whereas the repulsive potential was associated with the obstacles, and these obstacles are going to push the robot away so that there is no collision happening. And when we combine the two, we get the whole potential, which is going to allow the robot to reach to the final position while avoiding the collisions with the obstacles. But this pictorial representation is not going to solve the problem. We have to find some analytical method for that. So for that reason, we are going to start from this expression that the overall potential U for that particular configuration is equal to the attractive as well as the repulsive potentials. And then we have to find out how this attractive potential is going to be structured. So we explored that, and on the basis of that, we found out that there can be candidate functions, multiple of those. But out of those multiple possibilities, we observed that there was one called conic well, and the other one what we called parabolic well. And there can be others as well. So in a conic well potential, we found out that there is going to be a simple, straightforward representation, which is going to allow the robot to start from a higher potential and eventually reach to the goal location. But there was one problem associated with that. As is the case for all the approaches that you're going to explore, there are going to be certain merits and certain demerits associated with them. So with this, we observed that there is a discontinuity problem at goal location. So we explored another possibility that was parabolic well potential, and in that as well there were certain benefits, but there was one problem with that it grows unbounded when away from goal. But in this particular observation, you can readily identify that conic well potential is uh, very good when you're away from goal, and parabolic well potential is good when it is nearer to the goal. So why can't we add them together? Why can't we add these two uh, potential fields to construct some sort of a hybrid potential field? And that was explored last time. So this was possibly a hybrid approach can be possible. And we explored that. Similarly, for the repulsive potential, we observed, let me use a different color, we observed that for all the obstacles, you are going to find out certain region of influence. And that was the first point in that observation. So radius or region of influence. For each obstacle is what we need to define, and that was defined like a row. And then we found out one case structure which says that when something is away from that region of influence, you are going to have the repulsive potential to be equal to 0. When rho of that particular individual frame for that particular configuration was uh, away from this rho naught, let it be like rho naught indicated, and it is going to be one expression that we wrote last time when otherwise. So in that particular scenario, you can see that now you can define the attractive and repulsive potentials. And in order to make the robot move from the highest potential to the lowest potential, we went through quite a few details, eventually finding the expressions for the attractive forces as well as the repulsive forces. But these attractive and repulsive forces were corresponding to the Denvert-Hartenberg coordinate frames that we already decided. But this was being done on the basis of finding the negative of the gradients of this attractive and repulsive potentials. So we use these expressions over there. And the idea was to find the minima, so that the robot moves from the highest potential to the lowest potential. And the other thing that we realized was that we defined these potentials in the workspace, not in the configuration space. So with this realization that we have these expressions already figured out, and we all, by the way, use those expressions eventually on the application side on a very simple but effective uh, two-link manipulator example. And in that example, we realized that the attractive forces acting on joint number 1 were computed to be zeta 1, minus 1, and 1. And in order to make a physical realization of it, this would be something like that you have a force acting on this particular joint in the starting configuration having minus 1 and 1 vector. So this would be something like in this direction, like an attractive force which is going to try to make the robot move to the final configuration. And that is exactly what you can see is going to result in this change eventually. And let me use a different color for the attractive force acting on joint number 2. So you can see that that was corresponding to this vector, which is zeta 2 times minus 3 and 1. So what does that mean? So it would mean in its pictorial representation, this would mean that this particular point over here is going to be felt attractive with much stronger vector, which is going to be somewhat structured like this, that it is going minus 3 units along the x direction and 1 unit along the z direction. And we are assuming that zeta 1 and zeta 2 are in this particular case not having different values in them. So you can obviously see that if your joint number 1 is being felt attractive in this direction, and your point O2 is feeling attractive in this direction, eventually your robot is going to be parked in the final configuration like this. And we can see the physical realization of attractive forces as structured by the expressions that we derived last time. And similarly for the repulsive forces that we computed last time, you can see that the force repulsive acting on point number 2, O2, in the starting configuration was defined to be eta 2 times 0 minus 4. So in terms of its physical manifestation in a kind of a simplistic terms, so this would be kind of a vector heading in the y direction. So this would be somewhat like a long vector heading downwards. So which means obviously that this particular point O2 is going to be felt repulsed by an adjacent point B over here. Whereas for the other F repulsive acting on joint number 1, in the starting configuration, this was eta 1 times 0, 0, What does that mean? It means that this O1 is not going to be felt repulsed by this point B. Why so? Because it is away from the region of influence, because rho naught was considered to be equal to 1. So with this realization that you have got attractive and repulsive forces physically manifested as well, and you can make some physical sense of it, you can see that the robot is going to be starting from the starting configuration, feeling attracted and repulsed from certain directions, and on the basis of that combined effect, it will try to move to the final configuration. Now we have computed the attractive and repulsive forces acting on point O1 and O2 respectively, but there are still certain points which are needed to be looked into, and that is exactly what we are going to try to explore now. And for that, please see the attractive and repulsive forces listed over here. These we have already computed, but now these forces are defined in the workspace. But actually for the robot, which is going to have these joints, we need to transform these forces back to the joint space. And that is exactly what we need to do in the subsequent discussion. And for that, we have to understand the relationship between the workspace forces and the joint torques. And in order to understand that, we have to recall the differential kinematics. In that, you can recall that there was this end effector velocities to be equal to Jacobian times the joint velocities. And then we transformed that in order to have the inverse velocity kinematics structured, like Q dots were computed to be equal to Jacobian inverse times the given end effector velocities. So you can obviously see that in that particular scenario, the Jacobian was a linchpin between the workspace, which is over here, and the joint space, which is over here. So similarly over here as well, we have to see how these torques are going to be structured or computed when you have the forces available in the workspace. So in order to do that, obviously you are going to make use of a Jacobian, but this Jacobian is transposed Jacobians because how the forces and torques are correlated with each other. Now the other thing is that we are only considering the forces. So when we are going to only consider the forces, obviously this is not going to be a full Jacobian that will be required. It is only going to be the Jacobian for the linear velocity part. So for that reason, I'll write a little subscript over there. JV transpose times the forces that we have already computed are going to give you the joint torques. So these are joint torques, which can be computed when you multiply the linear velocity part of the Jacobian transposed times the forces that you have already computed in previous step, the attractive and repulsive forces. So let me write those down as well. Only considering forces, and these forces are going to be both of these attractive and repulsive forces. Now, that is the relationship between the two. So we are going to make use of this formula, this expression, in order to map the forces which are defined in the workspace into torques which are going to be felt by all those joints on the manipulators. We will consider the two-link manipulator again. We have the starting configuration of this manipulator to be like this. And we wish this manipulator to be oriented in this fashion in the final configuration. And on top of that, we have realized that there is one obstacle in the vicinity of O2, which is structured like this. Now, in order to accomplish the task up until now, we have seen the attractive and repulsive forces that we have already computed, but now we need to find out the joint torques on O1 and O2 so that the robot can have a better control paradigm implemented in order to avoid or implement all the motion planning. And for that, we have seen this expression that torques, which are the joint torques, are going to be equal to the Jacobian, the linear velocity part of the Jacobian, transpose times the forces. So in that sense, we have to find out these Jacobians. For whom? For two things. For O1, what is going to be that? And for O2, what is going to be that? So this is the quest initially that we wish to find out these Jacobian, and once found, we're going to multiply those with the already computed attractive and repulsive forces to find out the joint torques. So let's start with finding out the Jacobians. So the first step will be to find out this Jacobian for O1. And you can see that this is just like the way it is structured. You have this as theta 1 and this as theta 2. So you can simply write that one down. So this is going to be equal to, because it is a two-link manipulator, a 2 by 2 matrix where you have the very first one to be minus sine of theta 1, and this is going to be 0 over here because there is no influence of the second joint on this Jacobian. And similarly for the second row, you are going to have cos of theta 1, and then obviously you're going to have 0 over here. So this is Jacobian linear velocity part of the Jacobian for O1, which is over here. And then for the second part, you have Jacobian needed to be computed for O2 in a similar fashion, and that is going to be, because you can also recall that we have seen this example multiple times earlier as well, and there is one already recorded video for that as well when you have the 8 major problems indicated. So we have seen this thing earlier as well. So for two-link manipulator, when you have this as theta 1 and this as theta 2, and all the frames were defined with that, you have computed already these Jacobians. So I'll making use of that earlier discussion, I'll try to rewrite or recall that Jacobian. So that was something like minus sine of theta 1, similar to the JO1 first term in that, and then you have minus sine of theta 1 plus theta 2. All right, and then you had, for the second element in this row, you had minus sine of theta 1 plus theta 2. And then for the second row, you had cos of theta 1, and then you can have cos of theta 1 plus theta 2. So that is one part, and the other one is cos of theta 1 plus theta 2. So this was your Jacobian that you already computed earlier as well, and I've tried to rewrite that once again. So once you have got these Jacobians computed, you are going to make use of these in order to find out the attractive and repulsive torques. In the very start, the robot has to move from the starting configuration. So at QS, you have to see what is going to be the Jacobian. So this JO1 at QS is going to be equal to, when you plug in those values for QS in there. And what is that QS? It is 0, 0. So what does that mean? It would mean that you can have much simpler Jacobian over here. Minus sine of 0 is going to be 0. 0 is already over there. Cos of 0 is going to be 1, and this is going to be 0 over here as well. And similarly, for the Jacobian O2 at QS, you are going to have JO2 at QS simply structured like this, that you have minus sine of 0, minus sine of 0 plus 0, obviously 0, and then you have minus sine of 0 plus 0, which is also going to be 0, and then you have cos of 0 plus cos of 0 plus 0, which is going to be equal to 1 plus 1, which is equal to 2, and then you have cos of 0 plus 0, which is equal to 1 as well. So this is going to be the other part of the Jacobian. Now once you have got that, you can make use of that in order to construct the transpose, obviously. So JO1 transposed is going to be equal to, and let me use QS as well so that there is no confusion for that. At QS is equal to, when you take the transpose of that, so this is going to be 0, 1, 0, 0, and then you have JO2 transposed at the starting configuration, also simply written like 0, 2, and 0, 1. So now these are the two Jacobians that I'm going to use in order to construct or compute the joint torques. Now I'll bring forward the already computed forces over here, as well as the Jacobian that we have just computed. Now we are going to make use of this expression which says that the torques, joint torques, are going to be equal to Jacobian, which is the velocity part of the Jacobian transposed that we have already taken, times the forces. So we're going to make use of this expression to compute the torques. So the very first torque is going to be tau attractive acting on O1 in the starting configuration. Obviously that is going to be equal to zeta 1, and then you have the Jacobian O1 transposed, obviously, in the starting configuration times the F attractive force acting on joint number 1. So that is going to be equal to zeta 1, whatever that is selected by the user or by the programmer, times, then you have this already computed, which is 0, 1, 0, 0, and then you have F attractive 1 already computed, which is equal to minus 1 and 1. When you do that, this is going to be equal to zeta 1 times first row first column is going to be 1, and then you have 0 for the other. So this is your attractive torque acting in the starting configuration on O1. Similarly, you can do the attractive torque for the O2 in the starting configuration, and that is going to be equal to zeta 2, and then I can directly plug those values in, 0, 2, 0, 1 as the transposed Jacobian, times the F attractive 2, which is minus 3 and 1, so that is written down, is equal to, this is going to be zeta 2 times first row first column is going to produce, right, 2 and 1, yes. And then I can simply compute the repulsive torques as well on O1 in the starting configuration. This is going to be equal to eta 1 times JO1 transposed, which is 0, 1, 0, 0, times, actually the repulsive force is already 0 on joint number 1, so this is going to be 0, 0 over here, and that obviously is going to produce eta 1 times 0, 0. And similarly for the repulsive torque on O2 in the starting configuration is going to be equal to eta 2, and then you have 0, 2, 0, 1 as the Jacobian times the repulsive force on joint number 2, which is 0 minus 4. So 0 and minus 4 written down. So this is going to be equal to eta 2 times first row first column, this is going to be minus 8, and second row this column is going to produce minus 4. So these are going to be your attractive torques and your repulsive torques acting on O1 and O2 respectively. And if someone is interested in finding out the total joint torque, that can be computed by just adding these two factors together. And in this particular formula, you can see that appearing over here. We have assumed these zetas and etas to be equal to 1. So that is going to give you the total joint torque of -5 and -3 acting on the manipulator. There are certain other considerations as well. For example, what happens if you have multiple objects and sometimes the objects may not be convex. So in that case, you may not have the repulsive potential to be differentiable continuously. So in that particular case, you have to make sure that the region of influence of the obstacles are not going to overlap with each other. Otherwise, there is going to be a discontinuity in the middle. And sometimes your obstacles may be oriented in a fashion that they are much closer to other body parts of the manipulator, just like the one being shown over here in the diagram. So in that particular scenario, you may decide to have a floating control point added in the mix, which is not going to be your already selected Denver-Hartenberg coordinate frame. You can have another frame added, in other words. Now, this is the stage where we can formulate the path planning algorithm because we have already computed the total torques. We have already decided all the artificial potentials. So we can obviously formulate the path planning algorithm. And that would be something like this, that first of all, you have to determine your initial configuration. Once done, you have to find a desired point in the workspace. And in that case, you have to, using the inverse kinematics, calculate the final configuration. So step number 1 will give you QS and step number 2 will give you QF. Once done, you are going to locate the obstacles in the workspace and on the basis of that, consider all the repulsive potential fields. Once done, you have to compute the joint torques in the similar fashion that we have done for the case of two-link manipulator. Now, once done, you are going to use the gradient descent mechanism to reach to your target configuration. But what is going to be that? That is exactly the algorithm that we're going to define on the next slide. This gradient descent algorithm goes something like this, that you have to initialize it initially. And at that particular initialization stage, your starting configuration is going to be available, QS, and that is labeled as Q0. Now later you are going to, in an incremental fashion, keep on looking for this or keep on executing this process. And what is that process? That is that you have to check whether your current configuration QI at iteration I, when compared with the final configuration that you have already computed, and that distance comes out to be greater than the acceptable threshold or epsilon, you are going to compute the next configuration. And that next configuration is computed by using the previous configuration as one of the factors, and the other factor is like this. And what is that? This factor uses the torque that you have already computed in the previous configuration. So it gives you a vector towards that direction where you have accumulated torque computed. So what does that mean? It means that the robot is going to experience all those torques and those experiences are going to push the robot move towards that. So that would be the meaning of this expression, that it uses the current configuration and then it forces the robot to get into that direction based upon the experienced torque, joint torques, and then obviously you have to increment the iteration count, and if it is accomplished, then you are going to return all the configurations as a result of that. And if not, you have to then get back to, in an iterative fashion, keep on doing this whole process, eventually reaching to this final set of configurations. So this is going to be, in that sense, asking the robot to move on the basis of that gradient available to it, which is available on the basis of the accumulated torques, just like the way we have computed already in the example of two-link manipulator. With this gradient descent algorithm, there is a little problem that it may get entangled in a local minima situation. Generally, what happens is that when you have obstacles or you have corners in your workspace, your robot may get stuck in that configuration where it feels like it is the minima, but actually it is not the global minima. It is the local minima situation. So we need to find certain ways in which the gradient descent algorithm gets out of that local minima situation. So consider that possibly you may have your robot got stuck in the corner. So what is going to be the ideal scenario to get out of it? Possibly you may have certain kind of a randomized action added at that particular stage, and that may get the robot out of that difficult situation. So that is exactly what is going to be added in the gradient descent algorithm so that the local minima problem is avoided. Algorithmically, it would be first challenged to find out whether we are stuck in the local minima situation or not. So the answer to this question would be that check whether your successive iterations are going to give you minimum changes in the configuration. And if that's the scenario, that would be arrested by this statement. Then you have to find a remedial step. And the remedial step is that have a random walk to a configuration Q prime. And that random walk is quite simple to plan. It is something like you are going to have a random excitation added in the previous configuration. Just like the one being shown over here, you have V1, V2, all the way to Vn added randomly, generating thus Q prime, which is the random configuration in the vicinity of the previous configurations. So once you have found out that, you would move over there and then see whether your robot gets out of that local minima situation or not. And that is encapsulated by this red indicated part of the algorithm. So that is going to make your robot come out of that local minima situation if it is stuck in that. But if it is the global minima situation, eventually your robot will get back to that minima situation, and that would be assurance that you have got the final global minima achieved. Remember, potential field method is just like one of numerous methods available for motion planning. And in order to get a brief overview of available options, you can read this paper, and there are some other literature available on the topic as well. But in the subsequent discussion, we're going to have just like basic mechanisms of some of the other methods available. That is going to give you a kind of a overview of 2-3 other options which are available. One of the method is called D-star method. Actually, in this particular method, what happens is that the algorithm tries to find a path from the starting location, which is over here, all the way to the final location, which is somewhere over here, in such a fashion that it minimizes the cost of travel. So if the robot has to start its travel from this location all the way to the final location, it needs to find a path which minimizes that cost. So it is not going to be possible if each and every point, in this particular case, each and every pixel is going to have a specific cost associated with them. So generally what we do, we assign a very high cost to the obstacles, which are shown in red, and low costs to the open spaces. Just like you can go in diagonal direction, it is going to have some cost factor corresponding to it. And if you go horizontal or vertical, there is going to be some other cost associated with it. So when you have all the cost factors added or onto the occupancy grid, then you can ask the robot to find that path which minimizes the cost of travel. And in what you can do, you can download Peter Cox's Robotics Toolbox for MATLAB, and you can try such scenarios for your robots as well. You can do it for mobile robots, you can do it for manipulators as well. So that simple code is indicated as well. You can try that using that toolbox. So in a nutshell, you can consider this D-star algorithm to be an extension of A-star algorithm, but with a little twist that it has got to find out a minimum cost path from starting location to the final location, and it is going to be a graph-based approach. Another very popular approach is called probabilistic roadmaps. In that, you are going to start from the scenario where you have the obstacles available in the workspace. And then you have to create nodes, randomized nodes. But whenever a certain node is inside the obstacle, then you have to discard it, and you have to select only those nodes which are in the free space available. Now, once those nodes are available, then you have to connect them together using some sort of neighborhood functions. For example, one is being indicated like k nearest neighbor function. You can try others as well. There are numerous other neighborhood functions available, just like Moore's neighbors and von Neumann neighbors and all that. But whatever is that neighborhood function that you have selected, it is going to be used to connect these nodes together. Now, once you have all these nodes connected together, and by the way, you can see in this particular scenario, there are certain nodes which are not connected. For example, over here, over here. So you are going to have certain refinement steps taken, and that is going to be step number 3. In this enhancement step, you have to find out different schemes in which these nodes are well connected, and you have all the possible routes taken or connected so that you can later exploit them to find a better path from the starting configuration to the final configuration. So I'm assuming that you have in that refinement steps, you have connected all these nodes together reasonably well. And once done, you have in step number 4, start from the starting configuration QS and move all the way to QF while avoiding all these obstacles in the middle. You can try that using the Peter Cox toolbox, and the code is also indicated corresponding to that. So what you can do, you can try the same scenarios, and you can create those nodes. You can see whether these are well connected or not. For example, in comparison with A and B, you can readily see that B is not that well connected. You have this segment which is not connected with these segments of the nodes. So you can try different techniques to connect all these segments together so that you can find a path from the starting configuration all the way to the final configuration reasonably well. So you can try these commands which are available using the Peter Cox toolbox, and that is going to give you some practical realization of how this probabilistic roadmap is going to find a way out of complex scenarios. Guys, this is pretty much all that we wanted to cover in motion planning. Remember, this is a course on robotic manipulators, and we had to cover quite a few other topics as well. So this is just like the start of the motion planning activity. You can further take it from there, but in a reasonable detail, we have covered the potential field method and some other methods as well. We have covered the basics corresponding to a workspace and the configuration space. We have seen quite a few of those examples and applications as well, especially in the earlier case. We kept the discussion shallow, but in later cases we get into the details that how we're going to get the forces and torques, attractive and repulsive, all computed, and eventually which is going to be mapped onto the onto the manipulator, so that manipulator can start from a starting configuration and reach to the final configuration while avoiding all these obstacles. So I think this is it for now. Next time we're going to start a new topic. Until that time, bye bye.